All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Let's jump in here. Make sure I can see the chat here. Okay, looks like everything's good. All right, cool. Before I jump into this, maybe we should look at what we did last class. Did a lot of stuff last class, a lot of very vague things. First, we look at the intermediate value theorem. Super important theorem. And basically, it says kind of what you would think is obvious just by looking at a picture. But continuous functions will attain all intermediate y values, which means if you have a continuous function and you know that there's a value in between two y values on that function, then all values, y values in between those guys must also be attained. So if you have f is a continuous function, and you know that this is true, there is some value that's in between two of the other y values, then there must be an input in between a and b that will give you that value as an output. So that's called the intermediate value theorem. Now, one way in which that is useful, someone else coming in here. One way in which that is useful is it can tell us about, when solutions may exist on an interval if we know that we can describe the equation with a continuous function, right? Which is, besides actually stating the intermediate value theorem, this is going to be the way that we would test that you know the intermediate value theorem in a Calc 1 context. Pretty much going to give you an equation, give you an interval, and ask you basically prove that this equation has a solution in this interval. You don't have to find the solution. In fact, it might be very difficult to find the solution. So finding the solution isn't the point. You just want to show that it exists, right? Sometimes just knowing it exists means it might be worth looking for, right? If you think a solution doesn't exist, then you would just ignore it. But if you believe a solution exists, which the intermediate value theorem can help you with, it's worth looking for using some other method. So the idea is kind of bring everything to one side, or bring all non-constant terms to one side and set your f to be that function. If that function is continuous, which you might have to do a little bit of explanation about. In this case, it was a polynomial, so I didn't have to kind of explain that. We can assume that we know the elementary continuous functions are continuous on their domains. Polynomials, the domains is all real numbers. So once you have that the function is continuous, all you have to do is show that you can find outputs of that function that bound the constant that you care about from both sides. There's a y value that is above that constant, and then there's a y value that is below that constant. Once that is true, the intermediate value theorem will take effect, and you can prove that there must be an input, there must be an x value in between the inputs of two original y values, whose output will give you specifically that number. And once that works, it means that you have a solution to your equation, right? Because saying f of x equals 0 in this case is the same thing as saying this thing equals 0. So that would tell you that there's a solution to this equation and it's inside that interval. Some number between -1 and 0 will solve this equation. Now, I don't know what that number is. That's not the point. I was asked to show that there is at least one. So that was the intermediate value theorem, and that's how we can use it. It's one thing we spoke about yesterday. So the problem type here, like I said, I'll probably give you something like that on the first test. This will be the problem type. Pretty much show that this equation has a solution. And it'll be an intermediate value theorem problem. We also spoke about more on limits, properties that we've been using the whole time, really, about how nice limits are, about all the properties they have algebraically. And you can factor constants in and out. Limits distribute across sums, they distribute across products, they distribute across divisions. As long as you're not dividing by 0, they go in and out of powers. In fact, limits go in and out of continuous functions. And we spoke about that. We also spoke about the precise definition of a limit and how to prove that a limit exists according to this definition, for which I gave you a template, which is pretty much this guy. And I showed you how to actually fill that out. So make sure you know that. Spoke about, these are just other definitions using that epsilon delta kind of definition, but I probably won't ask you about that. But just something I should tell you about. Average rate of change, very important thing. Another thing that I will be asking you about. So an example that you should know here, the typical example, is I can give you a function and I ask you for the average rate of change on some interval. And basically what that is you take f of b minus f of a over b minus a, where b is the right endpoint of the interval and a is the left endpoint of the interval. You just do this calculation here, and that's the average rate of change. Now, what that tells you is how the output changes on average per unit increase in input, where a negative change would represent that the output actually decreased on average. We saw that the difference quotient, the guy that we were used to, is actually another way to express average rate of change. And we also saw that it could express the slope of a secant line. We also figured out a solution to the rate problem. We saw that in some ways, slope can be equated to speed or rate of change. And I chose a very suggestive example with very suggestive labelings of our axis. So you could immediately see that the answer was miles per hour. So you're like, oh, that's speed. But knowing that, we wanted to be able to do this in general. So we tried to figure out a way, how can we talk about slope in general if we don't have a straight line? And that was via something called a tangent line. And we want to know how to find the slope of that tangent line. Basically, we use a bunch of secant lines and then take the second point that the secant line went through and pushed it close to the first point, our point of interest. And that amounted to taking a limit as the distance between the 2 points approach 0, which is why we invented limits in the first place and make sure we knew how to understand them. So we called it the derivative, which was kind of out of character. But ultimately, we got to the definition of the derivative. And this is super important. You should know that, know how to state that. And yeah, let's talk about the notations. And we'll talk about further notation later on when we talk about higher derivatives, but that will be probably be a while from now. And then we did some examples where you wanted to use the definition of the derivative to find the derivative of certain functions. So whenever it is stated in this way, and yes, I will ask you a problem like this, use the definition of the derivative to find f prime for blah, or use limits to find f prime for blah. It means that I expect you to use this definition, this equation right here. We also did some examples, which were, I think, very important examples, because just knowing the answer to these examples by heart would actually be a good thing to do. So we used the definition to find what the derivative of x squared is, and we saw that that was 2x. And that's really something you should just remember. The derivative of x squared is 2x. The derivative with respect to x of x squared is 2x anyway. We'll see a distinction in that, I think, later today, if not early tomorrow. We also use that to find the equation of a tangent line. So once you can find the derivative at any point will give you the slope of the tangent line at that point, assuming it exists at that point, of course. And using the slope and the point, we can find the equation of a line, and that line will be the tangent line. So we also did that. And I also mentioned that this is something you should just remember. We also did some other things you should just remember, like we proved that the derivative of a constant is always going to be 0, no matter what the constant looks like. Could be a very ugly looking constant. It does not matter. The derivative of that constant is 0. We also proved that the derivative of a constant times x is just a constant, which makes sense because the slope of a constant times x is the constant, right? Slope of 3x is 3, slope of 5x is 5, slope of 7x is 7, right? So it makes sense that the derivative of a constant times x is just a constant, but we proved that in general. We can also get from this that the derivative of x is just 1. Something that was less obvious to us, we found the derivative of radical x, and that was 1 over 2 radical x. Again, something you should remember. It's a nice formula. And I asked you to try these, which they in and of themselves should be something you should remember. We're going to prove, we're going to do a lot of that. Like I'm going to do examples where I kind of show you how to get formulas that you should really remember them, but just show you where they're coming from. That being said, let's jump into these guys. So we are going to find f prime using limits, right? Find f prime using definition. So let's actually just jump into that. So we are in example D, f of x equals 1 over x. Okay. So now, remember your f prime, just the limit as h approaches 0, f of x plus h minus f of x all over h. We should know what that looks like. Here, that's going to be 1 over x plus h. Everywhere you see an x, you replace it with x plus h in parentheses technically, but it doesn't matter here. Minus the original function all over h. Okay, so how do we continue here? How do we take this limit? What do we do? The easiest way to do this, just assuming that we don't want to waste time on a test. What's the easiest way to do this? Anyone? Bueller? Well, yes, you would get 0 over 0 if you see this. But of course, that's not going to be the answer. There is an answer. So 0 over 0 is an issue. Like if I want to take this limit, what should I do? What do the strategies of limits tell me? So you get 0 over 0 if you just plugged in, right? Which is like step 1. So obviously that doesn't work because division by 0 isn't something we can do. So the next thing we should try is what? 1 over x plus h times x. What do you mean? Quickest way to simplify a complex fraction. Need to review our algebra, guys, or you're going to be in a lot of trouble. Multiply and divide by the LCD is the answer to that question. Easiest way to simplify a compound fraction, multiply and divide by the LCD. LCD in this case is x times x plus h. So this is going to be multiplying those two, and then we multiply straight across. So if I take x times x plus h and I multiply by 1 over x plus h, the x plus h's would cancel. So I'm just left with x in the first position. And if I take x times x plus h times 1 over x, the x's would cancel. So I'm left with x plus h in this position. Rookie mistake is to forget the parentheses. It'll happen a lot. So don't forget them. In the denominator, we would have hx times x plus h. Again, I will remind you, do not expand the denominator. So that's what we have. You'll notice now what's going to happen is you'd have x minus x here. And so what's left over on top is minus h over h times x plus h. Oh, someone said they were lost. Where did I lose you? Are you telling me that I lost the negative sign, or are you lost as in you don't know what I'm doing? I don't understand what that means. Yes, but where? What line did I lose you? You mean this line? Like the first one, or? Okay, so this guy here, the x times x plus h, it's called the LCD, is in least common denominator. Right, so the denominators in this fraction where you have h over 1, you have 1 over this, you have 1 over that. The denominators were 1, x, and x plus h. And you want to find the LCD of those. So the LCD is going to be the smallest expression, all denominators divide into. So that's going to be the product of all denominators factors where each factor is raised to the highest power which it appears. So that's like the LCD. So the LCD of those two things would be x cubed y to the 5th, because an x shows up and a y shows up, an x shows up and a y shows up, so you have to have an x and a y, and then you put them to the highest power. It's not okay to have an x squared because the x cubed is a higher power. So that's the LCD. Now, a compound fraction is when you have fractions inside of a fraction, right? So this is a fraction, this is a fraction, this is a fraction, and then we put all those fractions into a fraction. That's a compound fraction. The fastest way to simplify that is to find the LCD of all the denominators and multiply and divide by it. It's a strategy from algebra. So that's what I did. In this case, the LCD of the denominator is just the product of all the denominators. They were all raised to the 1 power. Right? This is to the 1 power. This is to the 1 power. This is to the 1 power. Okay. Now, when you do that, you will turn it into a simpler fraction in one shot. Pretty much every other method I know, it'll take you several steps to get from here to here. But doing the multiplying and dividing by the LCD thing gets you there in one step. So that's kind of how I would do it. You could do something like combine the fractions in the top, combine the fractions at the bottom, do the keep, change, flip thing. So you take the bottom fraction, you flip it and multiply. That's a lot of steps though. I wouldn't. You could do it that way. You'll just take longer to get to this line than I did, which if you're all about that, then please, by all means. But multiply and divide by the LCD, quickest way to simplify a compound fraction. Now over here, like if I were to have, the 1 over x plus h, and I multiply that by x times x plus h, which is the LCD, this guy will cancel. And so we're only left with an x. And similarly, if I have 1 over x multiplied by the LCD, the x times x plus h, then the x's would cancel, and I'd be left with the x plus h, which just goes here. After that, I just expand the parentheses, simplified. So hopefully you get that. That's what I'm doing here. At this point here, you can cancel those guys. And now you realize that you can plug in h equals 0, and you don't divide by 0 unless your x itself is 0, which we know it's not because x is not 0 from the beginning. Right? Of course, x not 0 here because you would have divided by 0 from the beginning. So we know that's not the case. So we can actually just plug in 0 for h. And we get -1 over x squared. And that's the answer. And by the way, this is just something that we know now. The derivative of 1 over x is -1 over x squared. Okay. So yeah, you need to go over your algebra rules. Like the section in pre-calculus or algebra where you had to compute a lot of difference quotients. You learned about compound fractions, how to find f of g of x, and how to simplify expressions like that. Yeah, so you should know when to multiply and divide by a conjugate, when to multiply and divide by an LCD, when to do something else, how to expand binomials, that sort of thing. So this is assumed knowledge. Now I know there are other ways to simplify this than the way I did it, but they're all longer. So I'd rather do it this way. But if you can do it properly another way, I'm all for it. But this is the way that I would do it. It saves you a couple steps. Let's move on to the next one. E. Let's find the derivative of sine of x. That's something to remember now. So similarly here, want to find the derivative. That is going to be the limit as h approaches 0 of f of x plus h. minus f of x all over h. This would be sine of x plus h minus sine of x all over h. Okay. So again, if we plug in h equals 0, you get 0 over 0. So we don't want to do that. We want to simplify. And I mean, sine of x itself, like this guy right here, well, how are you going to simplify that? That's what it is, sine of x, right? That is the simplest way to write that. H can't be simplified either. So the thing is, we'd want to be able to simplify this guy. So yes, again, throw back to pre-calc. What is that? What is sine of x plus h? Like, how can I rewrite that in a different way? Anyone? Euler? Well, technically, yeah, but that's way more complicated than we'd want. You're using like a wait. I don't even. Are you using like a sum to product formula? I don't think that would work here. But no, I think it's easier than that formula, whichever one you're thinking. So yeah, again, I do expect to remember your trick. So sine of a plus b, you should know is sine a cosine b plus sine b cosine a. If the signs are changed, it'll follow the sign. Cosine of a plus b is going to be cosine a cosine b minus sine a sine b. And if you change the sign here, it flips sign there. So with a cosine, a plus in the angle goes to a minus outside when you expand it. And so, yeah, these are called the addition formulas. And you're expected to remember them. So you're expected to remember SOHCAHTOA, right? Sine of an angle is just the opposite over opposite over hypotenuse. The cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. You should know the addition formulas for sine and cosine, the double angle formulas for sine and cosine, the half angle formulas for sine and cosine, but they're kind of the same as the double angle formulas. And yeah, stuff like that, like all these formulas that have to do with trig. So I'm going to use the first one on here. So this is going to be sine x cosine h plus sine h cosine x so that's what we have here by using addition formula for sine. Okay, so at the moment that might not look like it's simpler, but the fact that we don't have a sum in the angle is it's all good news. But now you'd realize that we kind of have a common term here. So let's pull that out. So this is sine of x times cosine of h minus 1. So we have that. Now I'm going to apply some limit properties that we have. First of all, algebra says that we can split a fraction across the numerator. So we know that. So I'm going to do that. This is this plus that, right? Because a plus b over c is the same as a over c plus b over c. And now we can take each of these limits individually because we know that limits distribute across sums. So that's what we're going to do. I'm going to be very suggestive here. Notice that the first one can be written as sine of x times cosine h minus 1 over h, plus here I could factor off a cosine, and I can have sine h over h. And it turns out now that these guys are actually things we would know the answer to. So this one here, as h approaches 0, what does that approach? Right, 0. Right, that's one of the special trig limits. What about this one, as h approaches 0? 1. Right, so this just becomes, well, sine x, because the h is not going to affect that. That's like a constant with regards to the limit. So you can factor it outside, times 0 plus cosine of x times 1. In other words, you just get cosine of x. Okay. So that gives us another rule. This is just, again, something that we know now. The derivative of sine of x is cosine of x. That's what it is. Now, of course, we're going to remember that. I'm not going to do it for you because it's very similar, just applying the trig formulas again. Similarly, we can show that the derivative of cosine of x is actually minus sine of x. And very important that you know that negative is there. Remember this. Okay. So these are some new formulas that we should remember. Derivative of 1 over x is minus 1 over x squared. Derivative of sine of x is cosine of x. Derivative of cosine of x is minus sine of x. Also, you should remember derivative of a constant is 0. Derivative of x is 1. Derivative of x squared is 2x. Derivative of radical x is 1 over 2 radical x. So these are all formulas that we should remember. Okay. Now let's talk about some properties of derivatives. So derivatives have a couple nice properties, not as many as limits though, but they do have some nice properties. So say here, let f of x, g of x be differentiable functions. Let c be a constant. Then the following hold. One, there is a property called the constant factor rule. And basically, this is very similar to that property of I'm starting to write clean again. Basically, this is similar to that property of limits where you can factor out constants. Basically, that says the derivative of a constant times a function is just the constant times the derivative of the function. Okay. That's the constant factor rule. So once I know how to differentiate a function, I automatically know how to differentiate any constant times that function. So for example, if I were to ask you, what is the derivative of 7 radical x, right? Well, this is the same as 7 times the derivative of radical x, which we now know what the derivative of radical x is. Right, so that's going to be 7 over 2 rad x, right? So if I know how to differentiate a function, I automatically know how to differentiate a constant times that function. You pretty much leave the constant alone and differentiate the function right beside it and multiply them together. Now, in practice, you don't really have to show this part. Right? You don't need to actually show that, oh, I'm moving the constant outside the derivative sign. It's just assume that you can do that. Like you just see a constant in front of a function, you immediately just leave that constant alone, differentiate the function. So you don't have to like write out the formula like that. Yeah, but that's the constant factor rule. And it pretty much works because it works with limits, but I guess I can talk about that after. Another property is called the sum difference rule. And pretty much that one is one that says derivatives distribute across sums and hence also against differences. So that is to say that the derivative of one function plus another function is the derivative of the first function plus the derivative of the second function. So derivatives can distribute across sums. And this goes with negatives as well. You just keep the same sign, actually. Right, so an example here is, let's say I were to ask you, what is the derivative of 1 over x minus the square root of x plus 5, right? So I can just notice that this is just going to be the derivative of 1 over x minus the derivative of radical x plus the derivative of 5. The derivative of 1 over x, we know that's minus 1 over x squared. We just did that. Derivative of radical x is 1 over 2 rad x. We did that yesterday. And the derivative of 5 is 0. So this is just going to be that. Again, I would say you don't have to show this line. But yeah, once you know how to differentiate a sum, once you know how to differentiate each individual term in a sum, you can differentiate the sum itself because the derivative will distribute across the sum. There's another example, just about something you should be aware. We can apply both properties at the same time. So it's not like if you use one, you can't use the other or anything like that. So an example of that is, what if I wanted to take the derivative of, say, square, a little bit more complicated, 4 square root of x minus 5x squared plus 2 over x, right? One, we know that the derivative will distribute across the sum. So this is going to be the same as the derivative of 4 radical x minus the derivative of 5x squared plus the derivative of 2 over x. Then we can apply the constant factor rule to get the 4 outside. Get the 5 outside. And get the 2 outside. And now individually, we know what each of these guys are, because I literally proved them for you the long way. So we can actually just find the derivatives of those guys. Okay. So again, I would say these 2 lines here, you don't need to show it. I'm doing it here for emphasis to show you that I'm applying the properties. Okay. You can literally just jump here. I'll know what you're doing, right? Leave the 4 alone, differentiate the radical x. Leave the minus 5 alone, differentiate the x squared. Leave the 2 alone, differentiate the 1 over x. You'll immediately get to this line. And I guess you can simplify this a little bit. So the 2 would cancel into the 4 to leave you with 2 in the top. 5 times 2 is 10. And we would have minus 2 over x squared. And that's the derivative. Right? So it turns out by knowing the derivatives of individual functions by heart, we can know the derivatives of more complicated things like constant times them and adding and subtracting them. So these are the 2 rules here. They're not hard to prove. I don't think I would prove them, even though I usually do, but it's the summer, so let's not worry about it. You want to know them, know that you can do this. And you don't have to write out that you're applying these steps, but just know in principle what it means. If you're finding the derivative of a constant times a function, leave the constant alone, differentiate the function, and then multiply them together. If you want to find the derivative of a sum, just find the derivative of each individual piece, right? Just kind of distribute the derivative. And you don't actually have to show that you're writing d dx, d dx, d dx, right? I'm going to know that's what you're doing or what you're trying to do or what you're supposed to do. And yeah, you will get there. Any questions on these examples here? Like how I apply these properties, how to get these guys. Okay. So those are 2 important properties of derivatives. They help us with a lot of calculations. So they help us to find derivatives of expressions where they might be multiplied by a constant and we have a bunch of expressions added together. If we know how to find the derivative of the individual variable pieces, we automatically know how to find the derivatives of all the others. So yeah, that's useful. That's it. Okay. Now, to throw back to something that I mentioned a long time ago, remember, if you feel like, oh, this would be nice if this could happen, and I didn't say that that could happen, then chances are it can't happen. What do I mean? It might be very tempting to think that the derivative would distribute across a product. So you might think, oh, if I have the derivative of f of x times g of x, can I just differentiate f and multiply by the derivative of g, right? Do derivatives distribute across products? And the answer is a very loud no. This is not correct, right? If something that nice were correct, I would tell you, right? But I ended the properties here for a reason. These two are very nice and they're true. It's actually derivatives do not distribute across multiplication. So, or if you, and multiplication and division are very similar. So if something doesn't work for multiplication, then it's not going to work for division. Well, so you might want to ask yourself, well, is the derivative of one function divided by another? Is that just the derivative of the top function divided by the derivative of the bottom function? And again, the answer is a resounding no. But we'll come back to these later. I don't know why I would write that in red. Okay, so just know derivatives, you can factor constants out and they distribute across sums. They do not distribute across products. They do not distribute across divisions. Okay, how you would actually go about doing these, guys, I will do for you later today, in fact. But before that, I also want to introduce you to a different rule. It's called the chain rule. Okay. So we're going to look at that first, something called the chain rule when it comes to derivatives. Again, this is something I'm not going to prove. I've done it in the past, but I just don't. We're already here for 3 hours. Let's not totally go crazy here. So here is what it says. Let f of x, g of x be differentiable functions. I remember what that means. It just means the derivative limit exists. You can find the limit as h approaches 0 of f of x plus h minus f of x all over h, and you'll get an answer, right? Same thing for g of x. Okay. Then here's the rule. The derivative of f composed with g. Okay, so you take a function and you plug it inside another function, right? How do you actually differentiate that? Well, here's what the chain rule says you would do. You would differentiate the outer function, leaving the inside function alone at first, and then you're going to multiply that entire answer by the derivative of the inside function. We can express that by this way: f prime of g of x times g prime of x. So this is the derivative of the outer function and leave the inner function alone. Right? Don't do anything to the g. Notice that the g of x didn't change in the first factor. Then you're going to multiply by the derivative of the inside function. Okay? So that's the chain rule. And this is, of course, provided that g of x is in the domain of f, right? So this just means we can compose them. We can take one function, plug into the other, and it's going to make sense because one is in the domain of the other. As long as you can form this composition and both of them are differentiable, you can differentiate the composition in this way. This is called the chain rule, super important rule. We're going to use it to differentiate, to derive a bunch of other rules. So it's a very useful rule in that sense. Almost, there are a lot of other rules can be derived using the chain rule to help us. Okay, so maybe I should give an example. What if I were to ask you, find the derivative of the sine of, say, x squared minus the square root of x? Right, so that is a problem. So now this is a composite function, you'll realize. Note, this is a composite function. Right? You can almost notice that there's an inside function and an outside function. And if f of x equals sine of x, it looks like the sine is on the outside, and inside of the sine, you plug in x squared minus radical x. So g of x is x squared minus radical x. Then f of g of x would be me plugging in g of x into the sine. Right? So that kind of shows you that this is a composite function, right? So it's not just sine of x, it's sine of a whole function. And so would you differentiate something like that? Okay. Now, this would give us, I think there's a delivery. Hold on. Okay, all right, we're back. I don't remember what that is. What did I order? Let's not worry about it. It's more important now to go over the chain rule. So, right, here is like sine, but something is plugged inside of it. There's something inside the sine. So what we can do here is find the f prime. You can also notice that that your f prime is going to be cosine of x, so we know that. And your g prime is going to be 2x minus 1 over 2 rad x, right? These are things that we found before. We discovered these rules before. So this says the derivative of this is going to be the derivative of the outside. The outside is a sine function. So it's cosine, leaving the inside alone at first. So that's the first part. This is like your f prime of g of x. Okay, so f prime is cosine of x, and you plug g of x into it, right? So just take the derivative of the outer function, which the outer function here is sine, and then leave the inside function alone at first, and then you are going to multiply by the derivative of the inner function, which we know is 2x minus 1 over 2 rad x. Now, obviously there's something missing here, or hopefully it's obvious that there's something missing here. You need parentheses. So this here is your g prime of x. Okay. So that would be the derivative. Some people like putting, because they don't want to mix up what's in the angle of a cosine. So usually when you have a trig function, you would put anything multiplying it kind of in front of it. So might be nicer to rewrite this as 2x minus 1 over 2 rad x times the cosine. So there's no ambiguity. Well, is the 2x minus blah inside the angle? Technically, it should be obvious, because if it were that case, I would put parentheses around here, but I didn't. But just to make it a little bit more clear, we can put the multiplier in front of the trig function. Very typical to write it that way. Any questions on this and the chain rule, like how it works, or this example? Okay. No? All right, so we'll move on. So one thing I want you to notice is that the chain rule, one nice effect that we have from knowing the chain rule is that it also allows us to generalize our formulas very nicely. So for example, I know that the derivative of sine of x is cosine of x. It turns out that I can get more general than that. So for example, instead of memorizing the derivative of sine of x equals cosine of x, and then you go on a test and you see something like this, and then you're totally confused with what to do, we can know by the chain rule. That I can know how to differentiate sine of anything. So u is just a function of x. So u represents anything. In this case, it could represent the g of x. It could represent like the x squared minus radical x. And we now know that we can write this as, notice what this looks like. This here was your g prime. And this here was the derivative of the outer function. So we can do the same thing here. I know whatever is plugged into the sine, its derivative is going to come out in front. And then I'm going to have cosine of the inside function. So this guy here is this is nicer to memorize. Because it can give you so much more bang for your buck by knowing that, right? The derivative of sine of u is u prime cosine u. And of course, it includes the original formula, because if u equals x, then u prime we know is 1, and so you get it back, right? Nicer to memorize, also includes the original formula. Since if u equals x, then u prime would be equal to 1. And so the derivative of the sine of x would be 1 times the cosine of x. And you'll get back cosine of x. So it includes the original rule, but it also can help you deal with things that are more complicated, like this guy. So that's the chain rule for you. And so, so it's nicer to memorize. You have a lot of nice things from here, the chain rule. 1, I think it's nicer to memorize this because you memorize more bang for your buck. 2, it will automatically include the original formulas that I derived for you. And 3, this is not like a benefit, but this is kind of like a recommendation. If you must choose between memorizing a basic formula and its chain rule version, memorize the chain rule version. It's the better one to memorize. So I know not everyone is into memorizing stuff. So if you can cut down on your memorization, it'll be nice. So if you're like, I don't want to memorize the version in X and the version in U, I would memorize the version in U because it also includes the version with X's. It's more general than the version with X, just the X, and it includes the version with the X. So I would memorize that. You can get away with a lot more. You can compute a lot more things. Okay. Yeah. So that would be a recommendation of mine, and let's continue. So we learned what the derivative was, why it's important, but now obviously you realize what I'm doing is I'm just teaching you how to compute certain derivatives, giving you certain formulas that you can use, giving you certain methods that you can use, because not every time am I going to ask you to compute a derivative by this long limit way, right? there are times when I'm going to ask you to be able to compute the derivative of a very relatively complicated function, and I want you to be able to do it quickly, not using limits. So ultimately, we can do this by learning some basic formulas, and then by building on those formulas with things like the constant factor rule, the sum difference rule, the chain rule, and some other rules I'm going to give you, right? And that will allow us to, by knowing the derivatives of each individual function, then if someone were to like combine all these guys into a more complicated function, we still know how to find the derivative. And so that's what we're doing. And we, without having to go back, to the definition. So yeah, that is the chain rule, a very helpful rule. So now let's talk about this is very differentiating exponentials and log functions. Let's talk about differentiating exponential and logarithms. And this could include our favorite ones, functions like e to the x, but others, it can include our favorite logarithm like ln x, but also others. So we're going to deal with all of those guys now. And here's a useful fact. Here's something you can know. If a, b are greater than 1, then the following equation is true. Log to the base a of b. It turns out that you can take a reciprocal of a log, but you have to switch the base and the number being logged. Right? Which is very interesting. It's true. So, for example, well, why is that? If I set log to the base a of b equals c, right? What does that mean? We know that means that a raised to the c equals b. So what I can do now is I can, instead of logging both sides to the a, I'm going to log it to base b. Of course, log to the base b of b, well, that's just 1. We know that from how logs work, and we went over that in class. So we also know that the c can come down in front. Okay, so this means this is c times log to the base b of a is equal to 1. And so this means that c is equal to 1 over log to the base b of a. And our c, we already said, was log to the base a of b. So it turns out we can switch the base and the thing being logged in a logarithm by taking an inverse, which is very interesting that you can do that. So let's go find some other guys that we don't know how to find yet. So first, what is the d dx of an exponential, like a to the x? Okay. Let's figure it out. since we don't know what this is, it's like one word. We don't have a formula yet. So let's use the definition. So I know that if f of x equals a to the x, then our f prime, which is going to be the derivative of a to the x, that's going to be the limit as h approaches 0 of a to the x plus h minus a to the x all over h. We can apply the constant rule for limits. Well, let me rewrite this first before I do that. This is the same as a to the x times a to the h. I can apply the constant rules for limits and factor out the a to the x, because in the limit, h is the variable. So anything with x in it is a constant as far as the h is concerned. And by factoring that out, I would have a to the h minus 1 all over h. So now I'm actually going to find what that limit is, which is somewhat tricky. So here's how we're going to do it. So I'm going to do a change of variable. Let n, and I'm choosing n for a very special reason, equals a to the h minus 1. So with that, what that means is that n plus 1 is going to be a to the h. And this means I can do something like log both sides, base a. I remember for these guys, I know I can do this because a greater than 1. We know how to do with a less than 1. It just means there's a negative power there, which we don't have to worry about right now. And obviously, if a is 0, we never consider negatives. But obviously, if a is 0, then this is just a derivative of 0, which you get 0. So we don't have to worry about that. If a is 1, then this is 1. The derivative is 0. Don't have to worry about that. And if we get anything else is covered by a greater than 1. So a what's going on here? A less than 0 is not considered, because remember that can lead to all sorts of craziness like complex numbers. A equals 0 gives the derivative of 0, which we know is 0. A equals 1 gives the derivative of 1, which equals 0. We also know that if a is between 0 and 1, then we can use a to the minus x in as a placeholder. And of course, and use the chain rule. So I say all that to say, I only have to worry about the case where it's greater than 1, which is what I told you this formula applies. All right, so now I'm here. We know that log to the base a of a is just the log and the base are going to cancel. Okay, so what I can do now, also what I can say is note as h approaches 0, then n equals a to the h minus 1 will also approach 0. Because a to the 0 would be 1, and then you have 1 minus 1. So now, we can rewrite the above limit. Remember, this was a to the x times this limit right here, limit as h approaches 0. I'm going to change the variable to n. So as h approaches 0, it's equivalent to n approaching 0. And my a to the h minus 1, I replace that with n. And then right here, I realize that my h can be replaced with this logarithm. Okay. Now, you might be wondering, well, what can we do with that? Well, this is, of course, that right? 1 over x is the same as x. So I can take that and I can move it into the denominator, which is this by a log rule. This is n. That's a limit rule. And this is a rule that we get because the log is continuous. I can move the limit inside. Now, this guy is actually very interesting. You may not remember, but we've seen him before somewhere. Maybe it was 2 lectures ago. Ah, there. That guy, limit as n approaches 0 of 1 plus n over raised to the 1 over n power. Notice that that's actually what I have here. So that actually gets you e. Crazy, right? That e shows up here. E does that a lot. Now, I'm going to apply this formula up here that I can go from the reciprocal to that. I can switch these. Log to the base e, we know what that is. That is ln. And finally, we get this rule. The derivative of a to the x is a to the x ln a. This is just something we'll memorize now. We'll never do this again, remember. Now, there is a special case here. If we choose a equals e, this would mean that the derivative of e to the x is e to the x ln e. However, ln of e is 1. And so you end up with the fact that the derivative of e to the x is e to the x, which makes it a very nice function. It's the only basic function that's not 0 that is its own derivative, which makes this function special for a lot of reasons. Notice this also applies to chain rule versions. The derivative of a to the u is u prime a to the u ln a. And the derivative of e to the u is u prime e to the u. So derivative of e to a function is the derivative of that function times the exponential, right? So do a few examples. If I wanted to differentiate 2 to the x, well, that's 2 to the x ln 2. If I wanted to differentiate 2 to the x squared, well, that's 2x, which is the derivative of x squared, times 2 to the x times ln 2. If I wanted to differentiate e to the x, well, that's e to the x. If I wanted to differentiate e to, say, the square root of x, that's going to be the derivative of the square root of x times the original function. If I wanted to do the derivative of e to the x squared, that's the derivative of x squared times the original function. All right, so it turns out differentiating exponentials isn't that bad. So using that fun fact and the definition of the derivative, we could figure that out, which is why it's important that you know the definition of derivative. I know a lot of students don't really get that. Well, why do you force us to do the limit way if you're just going to give us shortcuts anyway? The answer is every now and then you end up with a formula for which you end up with a function for which you don't have a formula for, and you have to go back to the definition. So a lot of the formulas we have, we only know them because we went through the definition and figured it out. Yeah. Do I want to do the derivative of ln now? No, we'll talk about ln after. What we'll do now is we'll take a break, 10-minute break, and talk for a while. Hopefully you guys are still alive out there. Was there something I had to say? There is something I had to say, but I'll probably say it when we get back. So take a 10-minute break, and we will return in a little bit to our regularly scheduled programming. Yeah, see you soon.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. On with the show.
We're back. Let's continue. We have another formula to derive. So we just derived two very important formulas. We now know how to differentiate exponentials. So this is just stuff we know now. So you'll never have to derive any of these rules I'm giving you. So you'll only ever have to derive a derivative by the definition when the question specifically says that, right? So I'm definitely going to give you a question that specifically says that, hey, use the definition of derivative to define the derivative of this guy, right? I'm definitely going to do that. But if you don't, then if I don't say that, at any other time we're asking you to find derivative, you can use the formulas that I'm giving you, which is why I'm telling you to remember. The formulas with the properties, with things like the chain rule, will help you differentiate stuff like that. Let's talk about the logarithm. I was kind of veering off to the side there. What about derivative of ln x? And everybody's like, what about it? Like, I don't, okay. Let's actually deal with the derivative of ln x, the natural log. Very important thing to know how to differentiate because it's a very important function. So here's how we're going to do it. Set y equals to the natural log. Of course, we want y prime, which is the derivative of this guy. So here's one way we can get that. So we write, if y is equal to ln x, what it means is that e to the x, well, let me, can raise both sides to the e, and so I would get e to the y is equal to x. Right? So now what I can do is I can differentiate each side. Right? Because if one is equal to the other, then the derivative of their derivatives are going to be the same. So the derivative of e to the y, we just derived that. The derivative of e to anything is the derivative of the thing times the original function. So it's y prime e to the y. The derivative of x, we also know that, that's 1. So now e to the y is never 0, so we can divide by it. E to the y not equal to 0. And so we have that. But we realized that our e to the y was actually x. So this is just 1 over x. In other words, the derivative of ln of x is 1 over x. And yeah, this is just something that we know now. And again, this is also something I mentioned yesterday. Remember, when you're memorizing rules and formulas, memorize the entire rules and formulas. Don't just memorize a part of it. A lot of students would memorize only this part of the equation for whatever reason. I'd see them just, they would think ln x, and then 1 over x immediately pops into their brain. And so they make a lot of mistakes because of that. So there are times when they have the log of something and they would just like rewrite it as 1 over the thing, when that's not true. You have to be differentiating for that to work. And so then not memorizing the d dx in the formula actually causes them to make mistakes. Don't let that be u. So that's the derivative of ln x. So of course, chain rule version. Of course, the derivative of ln of something else is going to be u prime times the derivative of u, derivative of ln of u, which is 1 over u. So this is just going to be u prime over u. So that's a nice rule. Derivative of ln of anything is the derivative of the thing divided by the thing itself. Right, so that's a nice rule to remember. I'd probably remember that even more than the original one. Derivative of ln x is 1 over x, but that's included in the second formula. Maybe some examples would be nice. Example, if I wanted to differentiate the ln of, I don't know, radical x plus x squared plus 2 to the x, that is going to be the derivative of all of those guys, 1 over 2 rad x plus 2x plus 2 to the x ln 2 divided by that radical x plus x squared plus 2 to the x. So that's how you differentiate ln. That's, yeah, it's nothing. It's not that bad. If you, just to do a simpler example, if you have ln of, say, a constant times x, like say 5x, right? That is going to be the derivative of the inside divided by the inside. Notice that that will actually cancel. In fact, the derivative of ln of cx is always just 1 over x. For a multitude of reasons, not only by this rule, but because ln of cx, you can write it as ln of c plus ln of x. Ln of c would be a constant, derivative of that would be 0. So this is actually equivalent to just taking the derivative of ln x. So if you have just a constant times x, the derivative is still 1 over x. In general, right? And once your c is something that can be in the domain, it'll work out. Here's something, the derivative of, say, negative x. Let's put, if I put a negative x in there, then that's also going to be 1 over x. Now that's actually something I do want to deal with specifically. Need to discuss the derivative of ln of absolute value of x. It's going to be useful later today as well as later in the semester. By later in the semester, I mean like a week and a half from now. So what if I wanted to differentiate that? So remember what this would mean. There are two possibilities. There is the derivative of ln of x if your x is greater than 0. Remember, it's undefined if x is equal to 0, but in this case, it's the derivative of ln of minus x if x is less than 0. So if your x is less than 0, absolute value is going to turn it into minus x to make it positive. So we have that piecewise function. Now, based on what we have here, derivative of ln x, we know that's 1 over x. And based on what I just said up here, derivative of ln of minus x is also 1 over x, because you'll just take the derivative of the inside, which is minus 1, divided by the inside, which is minus x. The minuses would cancel. So you also get 1 over x. So it turns out that that is just 1 over x. Of course, if x is not 0. So if you're in a situation where you want to allow x to be negative, this formula will come in handy. So in fact, that is going to be a situation that we're going to want. What about this one? Power functions. So let's look at something like the derivative of x to the n. Right? So we want to be able to differentiate things like, you know, derivative of x to the 7, derivative of x to the 1000, derivative of x to the bajillion, derivative of x to the radical 2, derivative of anything like that, which would be very, very annoying to do by the definition, by the way, if you didn't realize. I mean, even x cubed is annoying to do by the definition, because you'd have x plus h cubed minus x cubed all over h. Then you'd have to remember how to expand a binomial cube. Get x cubed plus 3x squared h plus 3xh squared plus h cubed or something like that. And then minus x cubed, and then you have to go through the. And as you start increasing the power, it actually expands. And that's only for the integers. Like if you have x to the radical 2, what does that even mean, right? So we want to actually deal with this guy in general. Yeah. So we're going to do something very similar. Set y equals x to the n. This implies if I take the absolute value of y, I would get the absolute value of x to the n. And this is because we don't want to have to worry about whether x is negative or not. Okay, so we have that, which means right now what I can do is I can log both sides. Why would I log both sides? Because as I just mentioned, the power is going to be annoying. So if you had like x to the 1000 or x to the radical 2, that power is going to be annoying. But we all know from like forever ago, being last week, that whenever you have an exponential, you have a power that's giving you trouble, you can use logs to get rid of it. So that's what we're going to do. We're going to log both sides. Yeah. So this is going to allow us to bring this guy down in front. So here we just log both sides. Here, apply a log rule. Now what we're going to do is we want to differentiate. So we're going to differentiate both sides. All right, so ln of the absolute value of y. Remember the derivative of ln of the absolute value is just 1 over the thing, right? So yeah, that's nice that we have that there. But also notice that this y is a function of x. It's not just an x. So the chain rule applies on the left side. So this is actually going to be y prime times 1 over y. Here you're going to just have 1 over x. So now you'd have y prime. You'd multiply by y on both sides. But remember what your y was. Your y was x to the n. So this is going to be n times 1 over x times x to the n. That is going to cancel into that, n minus 1, because we know that when you want to divide things of the same base, you subtract the powers. So this gives you nx to the n minus 1. So now that's we know how to differentiate that. And this rule is actually very important. So it actually has a name. This leads to what we call the power rule. Power rule for derivatives. There is a power rule for integrals. So normally when anyone says the power rule, they usually mean the derivative version. I don't know of anyone who calls it the power rule. If they're using the power rule for the integration version, they'll say it out loud. Oh, the power rule for integration. But if someone just says power rule, they're talking about this guy. The power rule is this. Derivative of x to the n is nx to the n minus 1. That's the power rule. So yeah, that's something that we know now, remember. You can also note if x equals 0, then the derivative of this would just be 0, right? So assume x not equal to 0, right? And of course, you would assume here also that your n is not equal to 0, because 0 to the 0 doesn't mean anything. It's undefined. All right, so yeah, that's something called the power rule. It's a super important rule. In fact, all the rules that we've done so far, other than the exponential and log rule, and the trig rule, obviously, the trig functions, can be derived from the power rule. So, example, this tells you, for example, that the derivative of x cubed is 3x to the 3 minus 1. You take the power down, subtract 1 from the power. So that's 3x squared. In fact, that's just something you should know by heart. The derivative of x cubed is 3x squared. The derivative of x to the 7, well, that's 7x to the 6. You bring the power down, subtract 1. The derivative of x to the radical 2 is radical 2, x to the radical 2 minus 1. The derivative of x to the pi, well, that's pi x to the pi minus 1. It doesn't matter what the constant is. You move it down in front, subtract 1. That tells you the derivative of x to a power. Now, we can also derive a bunch of rules we did before. So if I want to, for example, find the derivative of a constant, notice that that is a constant times x to the 0, because x to the 0 is 1. And then I can leave the constant alone. And this is 0 times x to the 0 minus 1. That's just 0. So you can get, again, that the derivative of a constant is 0. You can have, we also looked at the derivative of x squared. Remember that was 2x. So we can get that again. We also looked at the derivative of radical x. Remember, here we could just rewrite this as a power, and that's just bring the power down, subtract 1 from the power. That's going to be 1/2 x to the minus 1/2, and you know that's your 1/2 radical x. Notice that a lot of these guys that we derived before, we can get much quicker. D dx, so very weird. D dx of 1/x, remember we did that. We could rewrite this as a power, bring the power down, subtract 1 from the power, z minus x squared. Minus 2, minus x to the minus 2. Which is exactly what we had before, right? This is minus 1/x squared. So the power rule is very powerful because there are a lot of things that you can rewrite as x to a power. So it's very useful in that sense. So yeah. What do we want to talk about now? So power rule, we know how to differentiate x to a constant power. Log rules, we know how to differentiate a logarithm. We know how to differentiate the natural log. What about some other logarithm? We can use a change of base formula. That's why that's useful for us. The change of base formula says we can put in any convenient base. Ln is a convenient base because we know how to do that. And ln of a is just a constant. So I can factor that out. So the derivative of ln x is 1/x. So you get 1/x ln a. So yeah, we know that now too. So the derivative of log to the base a of x is 1/x ln a. Remember when you remember. Okay. Example. The derivative of log to the base 5 of x is 1/x ln 5. We can also do the chain rule version. And that would be the derivative log to the base a of some function u. Well, that's just u prime. U prime over x ln over u ln u. U ln a. So example, the derivative of log to the base 7 of something else, x squared plus 2. Well, that's just going to be the derivative of that divided by that thing, x squared plus 2 times ln of 7. Okay, so we know how to differentiate logarithms to any base. We know how to differentiate exponentials to any base. In particular, the base e, the natural logarithm, and the natural exponential. Those formulas are nice. Derivative of ln u is u prime over u. Derivative of e to the u is u prime e to the u. We know how to differentiate power functions. Derivative of x to the n. We know how to differentiate the sine function, the cosine function. We know how to differentiate constants. Well, that kind of counts as x to the n. Yeah, so now I differentiate a lot of things. Let's go back to something that we were worrying about earlier. Back to the derivative of f of x times g of x and the derivative of f of x divided by g of x. Okay, let's go back and deal with those guys. So I didn't give them as nice derivative properties because they're not as straightforward as you might think. First, let's deal with this guy. First of all, I want you to note the derivative of f times g is not f prime times g prime. Not true. All right, so don't do that. Right, this is very wrong. And it's easy to see, right, to illustrate. What if I wanted to take the derivative of x squared, which I actually know is 2x, right? So this we know here. We actually derived it a couple ways so far. And then instead what I did was write x squared as x times x. And then I'm going to do the wrong thing and just treat this as the derivative of x times the derivative of x. Then I would just get 1 times 1, which is 1, right? Which is not the answer. Right? So differentiating each piece of a product is not the way to differentiate a product. It's incorrect. You can't do that. So what is the way? This is the way. I don't know if that was a great meme opportunity. Let's move on. You can't live life with regrets. Let's just go meme opportunity. I should remember this. This is not the way. This is the way. Okay. So how do we do it? How do it do? Well, we want to do something that we have no idea how to do. So what do? We go back to the definition. So I know that the derivative of f of x times g of x I want to put this under here. By the definition of the derivative, this guy is going to be the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x, g of x, all over h. All right, so now we need to find a way to do this. And how we're going to do it is we're going to pull that sneaky trick that math people do from time to time. Find a way to add 0 somewhere, so it's not going to make a difference because you're adding 0 to the thing, in which case what you're going to do is you're going to add something and then subtract it again, right? So back in algebra class when you were learning how to complete the square of something, that might be something you learned, then we're going to do that. So f of x plus h, g of x plus h. What are we going to add or subtract? See if I remember. It's minus f of x times g of x plus h. And I'm going to add f of x times g of x plus h. This guy is 0. So it's not changing anything for me to add that. However, it is going to be convenient. How so, Jhevon? Well, I'm going to split this into 2 fractions. That's fine, whatever. Now you're going to realize something. G of x plus h is a common term in the first one. I'm going to factor that off. I'm going to factor it off to the right. It's not going to matter, but for aesthetic reasons. So what I will have left over is f of x plus h minus f of x, factoring off the g of x plus h, plus here, the f of x is a common factor. I'm going to factor that out. And we know that limits distribute across sums and products. So I can take this limit here and literally distribute it across all of these guys. So this is going to be the limit as h approaches 0 of f of x plus h minus f of x over h times the limit as h approaches 0 of g of x plus h plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. Now, in this guy, h goes to 0. This whole thing we know goes to f prime. This whole thing goes to g prime by definition. And this thing is going to go to f. Right? Because h, there's no h's in it. So now what we end up with is f prime of x times g of x plus f of x times g prime of x. This leads to something that we call the power rule. the product rule. It's another important rule, the product rule. So basically, if f, g are differentiable functions of x, then the derivative of the product f times g, well, that's just going to be f prime times g plus f times g prime. That's called the product rule. So that's the rule we know now. We know how to differentiate products. So, example. If I wanted to differentiate x squared times sine x, I could, well, differentiate the first one, leave the second, plus leave the first, differentiate the second. So this here would be f prime times g plus f times g prime, where I'm thinking of the x squared as my f, and I'm thinking of the sine x as my g. So we can have that. So that'd be a derivative of that product. It turns out once we have this, we actually have the division, the rule for the division version much easier. We don't even have to go through the definition. What we can realize is that division you can kind of think of as multiplication by an inverse. So for example, dividing by 2 is the same as multiplying by 1 over 2. So that is really just a derivative of f of x times g of x to the minus 1. And now we can apply the product rule. So I'm going to differentiate the first function, leave the second function alone, plus I'm going to leave the first function and differentiate the second function. Now, how do we differentiate the second function? Notice that there's an inside function. G is an inside function. The outer function is the minus 1 power, right? So we have to take the chain rule into account. So we're going to differentiate the outer function, which we now know the power rule. The constant power is going to come down in front. You're going to subtract 1 from the power. Then you're going to multiply by the derivative of the inner function. Let's clean this up a bit. So this is going to be f prime times g to the minus 1 minus f times g prime times g to the minus 2. So this is like f prime over g minus f times g prime over g squared. Create a common denominator to be able to add these together. So this would be f prime times g minus f times g prime all over g squared. This leads to another rule. It's called the quotient rule because it's how we differentiate quotients, right? Math people naming things. Like the derivative was special. So if f and g are differentiable functions of x, g prime not equals 0, then the derivative of f divided by g is f prime g minus f g prime all over g squared. And that is the quotient rule. I want you to notice the order in the numerator matters. Because saying fg prime minus f prime g is not the same as saying f prime g minus fg prime. In the product rule, the order doesn't matter because you're just adding. You could have done it in any order. You could start by differentiating the function on the right, and then in the second term, differentiate the function on the left. Yeah, and it's not a big deal. But in the quotient rule, you have to remember the order. And there are all sorts of mnemonics for remembering this. I never really found any of them to be useful. Things like low d high minus high d low over low squared or something like that. The high function is on the top, low function is on the bottom. It's weird, but I literally remember this by like talking out the formula. It's the derivative of the top times the bottom minus the top times derivative of the bottom over the bottom squared. Like I literally say that out. I don't know why I decided to do that, but I've been doing that ever since I was a kid, and I'm not going to turn back now. No regrets. All right. So that's the quotient rule. We can use that to differentiate divisions. So should I do a nice example? Should I just do a random example? Let's do a nice example. So I'm not going to do this in blue. I'm going to do it in white because I actually want you to remember. So here's an example. How would you differentiate the tangent function, right? So that's one of the basic trig functions. We do want to know how to differentiate it. So let's do that. So the trick here would be to rewrite this. We know that we can rewrite all the trig functions in terms of sines and cosines. So tangent is sine divided by cosine. And then I can think of this as my f and this as my g and apply the quotient rule. So it's going to be the derivative of the top times the bottom, right? So this is f prime times g minus the top times the derivative of the bottom. This is f times g prime, right? We know that the derivative of cosine is minus sine all over the bottom squared. This here is g squared. screen just flickered. Okay, so what this is of course cosine squared here, plus, because of the minus times the minus in the second term, there's a minus times a minus here. So that becomes a plus sine squared all over cosine squared. So of course, we remember that cosine squared plus sine squared is 1. So you have 1 over cosine squared. We also remembered that 1 over cosine is secant. So this is actually just secant squared. So the derivative of tangent x is secant squared x. This is something we know now. Chain rule version. So if you want to take the derivative of tangent of something, some random thing, it's going to be u prime times secant squared of that random thing. And I would actually prefer you to memorize the second formula than the first formula, but you do you, boo. All right, so something else we'd want to derive, another example. What about the derivative of the secant function? So we'd actually do the same kind of maneuver, rewrite this in terms of functions that we know how to deal with. Secant is 1 over cosine. Now you could do the quotient rule here, but I'd probably do the chain rule. This is the derivative of cosine x to the minus 1. We're going to do chain rule. When the numerator or the denominator of a fraction is a constant, you probably don't want to kill yourself doing the quotient rule, which we'll talk about that later as well. So here, differentiate the outer function, multiply by the derivative of the inner function, and we have that. So we have essentially cosine to the minus 2 times sine, or that's the same as 1 over cosine squared times sine of x. This is customarily, you take a factor of cosine, move it over there, and 1 over cosine is secant, and sine over cosine is tangent. And so we get another rule. The derivative of secant is secant tangent. And this is just something we know now. Chain rule version. The derivative of secant of u is u prime, secant u, tangent u. So we know the derivatives of 4 of the basic trig functions. The other 2 I'm not going to derive, I'm just going to tell you what the answers are similarly. The derivative of cosecant x is going to be, actually it's minus cosecant x cotangent x. and the derivative of the other one, cotangent x, similar to tangent, but it has a negative. It's minus cosecant squared instead of the secant squared. So those are two rules. I don't think I'll ask you about cosecant and cotangent a lot. Sure, you need to know the basic rules, but in terms of doing calculus with them, I probably won't ask you to know those specifically. But if you didn't remember these formulas, you could always rewrite cosecant as 1 over sine, and you can derive the formula that way. Cotangent can be rewritten as cosine over sine. You can derive the formula that way by using the quotient rule. All right. What else do I want to do here? So, second account. We know the properties of derivatives. We know the chain rule. We know how to differentiate exponentials, general exponentials, as well as the natural exponential. We know how to differentiate logarithms, the natural log, as well as regular logs. We know the power rule, how to differentiate x to the n. We know the product rule, how to differentiate products of functions. We know the quotient rule, how to differentiate divisions of functions. At this point, there are no more rules for you to know. There are other versions of differentiation that I'll go over, like log differentiation and implicit differentiation. However, those you kind of build up based on the rules that we already covered. Like they're not rules in and of themselves. They're like more like methods where we apply these rules that we already know. So yeah, we're pretty much good for derivative rules at this point. And basically, with these rules that we've covered today, you can differentiate all sorts of functions, right? So I can go to town and give you guys some crazy functions to differentiate, and you guys will be fine. Yeah, it's nice. Maybe let's just do some examples just to find the derivative of sine x over x. Find the derivative of, say, x plus 1 divided by x plus 2. Find the derivative of, say, x squared over 2. Find the derivative of 3 over radical x. Find the derivative of 2x plus 1 to the 8 times x squared plus 1 to the 5th. So it's 1 to the 8 divided by x squared plus 1 to the 5th. ln of this guy, 2x plus 1 to the 8th over x squared plus 1 to the 5th That'll work as a primer for a log differentiation. Differentiate. So, I shouldn't say differentiate the following there. I already put a derivative in front of it. So I'm like evaluate the following. There they are at a glance. So you can take a picture if you want. Give you a few seconds to do that. And then we're going to kill all these problems. All right. So after these examples, what did I want to do? Do I want to start it? Let me add a couple more. So I already told you guys about the chain rule H. I it'd be nice to segue into the next section, I think. I want to talk about the existence of the derivative next. I think so. So this will be a nice segue. If f of x equals the absolute value of x, compute f prime of 0. No, I don't need that much space for those guys. Okay. That's them at a glance. After doing this, I don't think we're going to do anything else. Let's go. Let's put what we learned into practice. Okay, so we're going to differentiate this. Let's take a deep breath, maybe grab a drink. And let's do it. So one of the problems on the test, which I guess is something I wanted to talk about. When is the, let me make sure. I think we have a test very soon, actually. Test one is June 11th. So yeah, it's coming up very soon. So the test is going to be on Friday, which I know we don't have class, but I wanted to give you guys a day. So it will be a 24-hour window. So something like Friday morning to Saturday morning, and hopefully you can find time in that 24-hour window. Yeah. I actually wouldn't mind to push it a day, but I'd have to know that everyone would be able to do that. So something like Saturday morning to Sunday morning. Yeah, I don't really care either way, but you guys might want an extra day to kind of absorb all of this. So maybe I will send out a poll. No, I mean, there are very few of you in the class. It's a very small class. So maybe I'll just send out like a mass email or something and ask you to send me an email if you can't do it. And then we'll just keep the date that I had before. But yeah. Let's just get through these. So this guy here, we have a division. So probably think of this as an F and a G. And I know that the derivative of F over G is F prime G minus F G prime over G squared. So that's the quotient rule. That's what I'm gonna do. So the derivative of the top function sine is cosine times G, which is X, minus the top, which is sine of X, times the derivative of G, which is just 1, all over G squared, which is X squared. So this is just going to be X cosine X minus, that's kind of weird, X cosine X. Why is it doing that? X cosine X minus sine X all over X squared. That's the answer. So the thing is with practice, finding these derivatives of these random, there's something on my screen, find derivatives of these random functions that I give you. There's going to be a problem on the test where, again, just like with limits, I'm going to just give you several problems like A, B, C, D, or A, B, C, D, E. It'll be 4 or 5. where I just give you a function and say, find the derivative. And you're just going to go through and do whatever you got to do to find the derivative. Might be chain rule, might be product rule, might be quotient rule, might be any of the above, mix and match. There are problems where you'll need several of the rules. In fact, there are examples here that I gave where you will need several of the rules. So yeah, so being able to differentiate functions quickly is something that you'd want to be able to cover. And if you know the rules very well, it shouldn't be too bad. This one, probably the same thing. That's my f, that's my g. I know that the derivative of f over g, one way to know the rules is that every time you're using them, write it down, is going to be f prime g minus fg prime over g squared. Pretty soon, if you get enough time to practice, which in the summer is hard to get a lot of time to practice. I mean, your test is in a couple days after we're learning this stuff. But you'll be able to actually just do it on the spot without having to write out the rules separately. But that takes a little bit of practice. Maybe by the final comes around, it's very possible for you guys to get to that level. But if you on test one, you're not at that level, it's fine. Just write the formula in the top corner and then just apply it. Just do a paint by numbers thing. Right, so this is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So this is x plus 2 minus x minus 1 over x plus 2 squared. Now the x's die. 2 minus 1 is 1. So that's that one. Give me a few minutes. I'll just do the typical thing. Paste the link to the lecture notes yet again in the chat. In case at this point of the night you're just brain dead and you're barely hanging on, you're like you can't write and listen at the same time, you can follow along in the notes there. Now this one is interesting. The denominator is a constant. So here I would recommend that you don't do the quotient rule. Just think of it like that. You can always factor the constant off. And that's just going to be a half times 2x, which is just x. Or notice that what I did kind of amounted to just leaving the 2 in the bottom and then differentiating the top. And I would use this as a tip for the derivative of f over g. If g is a constant, do not use quotient rule. just leave G alone and differentiate F. It wouldn't be wrong to use the quotient rule, but in cases where you don't strictly have to use the quotient rule, but students try to use the quotient rule, I see them get it wrong a lot of the time. And usually it comes from the fact that they forget that the derivative of a constant is 0 while they're doing the quotient rule. Like they're trying to do the quotient rule, but then one of the functions is a constant. For whatever reason, students tend to rewrite the constant instead of writing 0 for the derivative. I don't know why that happens, but it happens a lot. I've seen it happen a lot. So one, it's easier to do this than to do it with a quotient rule. And two, you're kind of saving yourself from potentially making a mistake. So if the denominator is a constant, I would not do the quotient rule. I would just leave the denominator alone, differentiate the numerator. Similarly for this one, I would not use the quotient rule either. I would, if there's a constant on top, what I would do is I would rewrite it by bringing this guy up. Right, so this guy is and then we know we can leave the constant alone, differentiate that guy. To subtract 1 is same as subtracting 2 over 2. So that's going to be 3 over 2 minus 3 over 2 here. And I would say again as a pro tip, in the derivative of f over g, if f is a constant, do not use the quotient rule. What I would do is bring g up. So as f times g to the minus 1. Let me just be a little bit safer here. Put g in parentheses to the minus 1. And use chain or power rule. In this case, we could get away with the power rule, but in general, I would say you would need the chain rule. So that's that one. This one here, you have this is like your f, that is like your g, and we know that the derivative of f times g is f prime g plus f g prime. So that's what we're going to do. Differentiate the first one. We need the chain rule. Differentiate the outer function, which means bringing the power down, subtracting 1 from the power, and multiplying by the derivative of the inside, which in this case is just 2. Then you leave the other function alone. So this here is f prime with chain rule. And this is your g. Plus, you're going to leave the f. Then you're going to differentiate the g, which again is a chain rule thing. So this is f, this is g prime with the chain rule. At this point, Strictly speaking, you won't have to simplify here, but I'm going to simplify because in the other one, I'd want to simplify, as well as later on. There are going to be reasons why we want to set the derivative equal to 0. And so if you have expressions like this spread out, you'd want to factor them to solve for what x values make it 0. So what I would do here is I would factor, which means we need common terms. Notice that 2x plus 1 is a common term. X squared plus 1 is a common term. 2 is a common term. Those are all the common terms. So remember how you factor stuff. You pull out the common terms to the lowest powers to which they appear. So 2x plus 1 to the 7, I have 2x plus 1 to the 8th. I would pull out 2x plus 1 to the 7th. I have x squared plus 1 to the 5th, x squared plus 1 to the 4th. I would pull out x squared plus 1 to the 4th. I just have 2, so I just pull out 2. And then, right, what we have left over. So I left the 8 inside, and I pull out all 7 factors of that guy, and I pulled out 4 factors of the x squared plus 1, so there's only 1 factor left. I pulled out 7 factors of the 2x plus 1 to the 8th, so there's 1 factor left. The 5 stayed, and the x squared plus 1 to the 4th I pulled out, the 2 I pulled out, so there's an x left. So this is 2 times 2x plus 1 to the 7th, x squared plus 1 to the 4th. This shouldn't be a 5th power. This would be 8x squared plus 8 plus 10x squared plus 5x. $18x squared plus 5x plus 8. And that's that one. This one is f, that's g. So we can do, again, the quotient rule. You know that the derivative of f divided by g, f prime g minus fg prime over g squared. So we can do that. F prime, 8 times 2x plus 1 to the 7th times 2 times g, x squared plus 1 to the 5th, minus f, 2x plus 1 to the 8th times g prime, 5 times x squared plus 1 to the 4th times 2x, all over the bottom squared, which is x squared plus 1 to the 10th. Again, want to pull out common terms. 2x plus 1, the 2, the x plus 1, x squared plus 1, 2, 2x plus 1 to the 7th, x squared plus 1 to the 4th. We are left over with the 8, x squared plus 1 minus 2x plus 1 times 5x. Looks like over x squared plus 1 to the 10th. This cancels out 4 powers of that. So we have 2 times 2x plus 1 to the 7th, 8x squared plus 8 minus 10x squared minus 5x. This is minus 2x squared minus 5x plus 8 all over x squared plus 1 to the 6. That's the answer. Oof. Yeah. So I will leave the rest for you guys to do because we're pretty much out of time now. So, and of course, since we have a test coming up, it'll be good practice to see if you actually understand the rules that I went over today. You're going to want to do that. Also, I should probably give you, open the homeworks for this chapter as well. So the homeworks for chapter 1 have been up already, but I'll put in the homeworks for chapter 2. I think we're in chapter 2. Yeah, so we'll stop there. We did a lot. From G onwards, you'd want to do, so that's these problems right here. And yeah, which you have the notes, so you can see them there. And we will we'll stop there. Okay, so yeah. Hopefully that wasn't too crazy, but it's the summer. It's going to be crazy anyway, especially since we have a 3-hour class. It's going to feel, your brain's going to slow down after like an hour and a half. Happens to everyone. Would even happen to me. So yeah, it wasn't my idea to do the 3-hour class. I think it's a much better option to do it like an hour and a half and just stretch the summer to 2 months. You'll still have a whole other month, but whatever. I don't make the rules. We're here, let's make the best of it. Hopefully that was clear and not too bad. And see you guys in the next one. Ciao.